I think we are indeed live. I hope. Welcome, everyone. I think we are.
Yes, we are live.
Okay. Pardon some technical mishaps right now at the beginning. We are starting this.
We are live.
We are indeed live. Perfect. I hope you can hear me well. I'll just like to say welcome again to everyone. My name is João Faria. I am a researcher at the Institute of Astrophysics and Space Sciences in Porto and in Portugal. I am here accompanied by my colleagues to tell you a little bit about this announcement that we did yesterday. So we have Alejandro Suarez Mascareño, Mario Damaso, Francesco Pepe is also joining. We are very happy to be here today. I will take a couple of minutes to make sure that we are all set up and that we start getting people to watch. And maybe I can tell you why we are here today during that time. So you probably noticed and you saw that yesterday we we made an announcement of the discovery of a new candidate exoplanet, Proxima D, we called it. And we are here today to give some details, to talk a little bit about this discovery on a slightly more technical aspect, but also to just hear your questions and hear whatever comments people may have about this discovery and tell you a little bit more about the story. I think we are going well. So it is. Alejandro, is everything okay? Can you confirm?
Yes, we are live on Twitter. We are live on YouTube, and there's around 30 people watching it on YouTube, and I don't know how many on Twitter. So at least it's working.
Perfect. I think this is much harder than finding exoplanets, or at least as hard, but we are managing. Okay, so maybe we can start. We have a small presentation, a very short presentation that we're going to go through. All of us will talk a little bit about specific aspects, and then at the end, let's say in about 10, 15 minutes, maybe less than that, we'll take questions, any questions. Feel free to, if you are joining, if you are watching on Twitter or on Facebook or on YouTube, feel free to comment. I believe we will be able to see your comments arriving. So feel free to interact with us through that or through any other means you find. And maybe we can start the presentation, if that is possible.
Yes, give me a moment. It should be there now.
Yes, let's put it full screen. Okay, this is perfect. So again, welcome everyone. It's really a great pleasure to be here, showing you or telling you a little bit more about this candidate sub-Earth planet that we found orbiting Proxima Centauri. So I thought about going through quickly. I think we all know our stellar neighbor quite well already, but let's go a bit to the next slide to show you just the basic properties of this star. What is this star, Proxima Centauri? It is part of a triple star system. Is a third star together with Alpha Centauri and Alpha Centauri B. And it's indeed the closest star to the Sun at just 4.2 light years from us. This is an M dwarf, as you probably know, and it's smaller, less massive than our own Sun. And it's basically red, and because of its lower temperature. Although we also pointed out here that this is sometimes something that comes up, which is the habitable zone. What is this? Is just the range, the kind of the distances from Proxima where water can have a liquid state, can be in a liquid state. And so we quoted that here in terms of distance in astronomical units to the star, and also in terms of what this corresponds to in an orbital period of planets. So then we have the star, we have the host basically of this show, and in the next slide I will show you what we did, what we observed, and what kind of data we obtained. So in the next, yeah, there we go. So what you see here are the ESPRESSO observations of Proxima. We'll talk a little bit about ESPRESSO in just a minute, but here are the observations, the raw radio velocities. We have measured how the star moves back and forth and what is its radio velocity. You see here actually two graphs, one on the left and on the right, and they are just different radio velocities that were derived using two methods. One of those methods is a cross correlation with a mask, which is a more typical method to obtain radio velocity from the stellar spectrum that we actually observe. And then on the right graphs, you also see the same for template matching, which is another also typical method to derive RVs, which instead of using a mask, just compares spectra to each other or to a template. I also note briefly that we divided the data set into these three chunks, and we can discuss that a little bit more, but there's three chunks of the same ESPRESSO data. Here, just to note that the template matching seems to provide improved radio velocity precision. On this case, it's quite common that this happens for M dwarfs. But otherwise, the RVs are similar, and they are in agreement with it between the two data sets, between the two techniques. And so using these data, these are 114 ESPRESSO observations from 2019 to 2021. What we managed to do, and I will show you in the next page, is to actually find a signal, a periodic signal that you see. If you look at the right graph here, what this shows is the posterior distribution for what orbital periods, what signals might be in the data. And you show very clearly two peaks in these two very high probability signals. You see one at 11.19 days, and that's Proxima b, the first planet discovered in this system. And then you see also a second one at 5.12 days, which is the new candidate Proxima d. So this is the signal that we were able to find in this data. A bit more specifically, we managed to use one extra piece of information that we have, which is the full width of maximum of the CCF. We can go over some details of what that is, as an activity indicator. That's because the star, Proxima Centauri, is not a quiet star, let's say, and it does show strong stellar activity, and so we have to account for that. The full width of maximum here that you see in the bottom graphs helps us to identify, to separate what is stellar activity and what are planets or planetary signals. I would highlight next that on the residuals, so once we consider a model that contains stellar activity and these two planetary signals, we are able to achieve a final root mean square, final residual variation of just 27 centimeters per second. And this is quite an achievement, and it's only possible because of the excellent data that ESPRESSO is providing. I will just go briefly. So there is this new candidate, and in the next page, I will show you what this candidate is. What is this planet? If it's caused by, if the signal is caused by a planet, this would mean it has about 25% of the mass of the Earth. That's 1/4 of the mass of the Earth, and it's at 0.029 astronomical units from Proxima Centauri, from the star. That means that it's outside the habitable zone as we defined it before, unlike Proxima b, the first planet. But it makes this a very interesting detection in terms of knowing this planetary system. So you see here some of the constraints that we were able to put on the properties of the planet. In particular, I can note the semi-amplitude, which you see here highlighted as with a K letter, and we are talking about 38 centimeters per second. And this, again, is a huge achievement because we are going down in precision. We are being able to detect lower and lower amplitude signals, which translates into lower and lower mass planets. You see here the phase curves for the two signals. That is just phase folded on their respective periods. You see they look quite nice together with the ESPRESSO, with the three subsets of ESPRESSO data. And that's it for Proxima D, at least. Let's now go through to the next, and Alejandro will talk a little bit about the other planet, Proxima B.
Thank you, Joao. So what I'm going to show it's now a very nice artistic representation of the inner part of the Proxima system, in which Proxima D, which is the dark small dot at the left, is joining the worldwide famous Proxima B, which was the habitable zone Earth-like planet detected in our nearest star in 2016 that we managed to confirm in 2020, also using ESPRESSO. And I think this is becoming a really exciting little system with now an Earth-like planet potentially habitable. That's still to be discussed. A very small planet, one of the smallest known yet, and they are not alone. There's also even a third planet, and we have here with us Mario Damaso, who was the lead author of the paper that found it, to tell us also a bit about that one. So I let Mario now speak.
Okay. Thank you very much, Alejandro, and hello everyone from Italy. Yes, the story about Proxima C dates back to 2018, a little bit, almost 2 years after the announcement of the detection of Proxima B. What we did at the time, we didn't have ESPRESSO yet, observing the star. And so we reanalyzed the data, published it, and some more radial velocities with the goal of looking for something more in the system after Proxima B. So what we proposed as a candidate, because the planet, this Proxima C has still to be confirmed independently, what we found is the evidence of a signal, as you can see in the right upper right panel, in the radial velocities, a signal that we attributed to a planet with an orbital period of a little bit more than 5 years, and a minimum mass approximately of 6 Earth masses. Maybe what you can appreciate here in these plots are compared to the radial velocities that my colleagues just showed you from ESPRESSO, is the difference in precision and quality between the two data sets. The other plots are just to mention that even if this planet is still a candidate, by the way, after the detection with the radial velocities, Proxima C stimulated some other studies. For example, getting observations with a sphere instrument for direct imaging, and even to go back to archival data, astrometric archival data taken with Hubble to look for evidence of astrometric signals. At the moment, this data cannot rule out the planet, but and provided even some more information more. But the existence of Proxima C, at least even in the radial velocity, is still to be proved.
Okay, so I think now after this summary of the status of the planetary system of Proxima, we are going to jump to discuss ESPRESSO a bit. And we have Francesco Pepe, PI of the project, to discuss it a bit.
Can you hear me, Alejandro?
Yes, we can hear you.
Yeah, so thank you very much, and congratulations to all of you for this beautiful work with ESPRESSO. And as you said, this discovery has been made with the ESPRESSO spectrograph, which is an instrument to observe through the Doppler effect to measure stellar velocities at a precision which is for me, even for me, still unbelievable. Okay, you try to understand the speeds, motions of the star, which correspond to the speed of a walking person. Well, this ESPRESSO instrument is actually the continuation of the development of spectrographs based on the technique and the instruments used by Michel Mayor and Didier Queloz in 1995 to discover the first exoplanets ever. And in the meantime, this instrument and the technique has been improved to a precision which is just unbelievable. So ESPRESSO was built in this continuation for ESO, the European Southern Observatory, and for the Very Large Telescope, the VLT. It's a consortium of institutes in several countries, from Spain, Portugal, Italy, and Switzerland, in collaboration with the European Southern Observatory. This instrument was built, delivered to the observatory in exchange of observing time, which started in 2018, in the 1st of October. And what you see here is this beautiful site, the ESO Paranal Observatory in the northern part of Chile, with these 4 8-meter telescopes. And ESPRESSO is just installed in the cellar of these telescopes and can actually collect the light of any of these big telescopes or even the 4 telescopes at the same time. And on the right side of this slide, you see a spectrum, a raw spectrum, as it will be provided by the instrument. Of course, you cannot read directly from the spectrum the radial velocity or the velocity of the star. So there is a data analysis machinery behind which will then provide the data that have just been presented to you. So I will stop here, just referring to the table if somebody is interested in what are the performances, the spectroscopic performances of the instrument, which, as I said, are really amazing. ESPRESSO belongs to the best instruments in the world to do this kind of work. Thank you, Alejandro.
Thank you, Francesco. And now, was this the last slide, I think?
It was indeed, yes. We can go to the... I think we are finished with our presentation. Maybe in the next slide, we have a small highlight, let's say, and which is not completely showing correct, I think, but we are indeed open now to a Q&A, to a small session of whatever people are interested to ask us directly about the planets, about the star, about ESPRESSO. Just as a very tiny Okay, just the take-home messages. I was just going to say, there's a new planet candidate in Proxima Centauri with a minimum mass about half the mass of Venus, and this joins. That's the exciting part. Also, I think is there's now a full system of planets, Proxima B, C, D, around our closest neighbor. So yeah, maybe let's open the Q&A. If we already have questions, and feel free. I think you can ask us your questions in all the platforms, if I'm not mistaken. So feel free to do so.
I think the questions in the YouTube channel appear directly.
Okay.
And the ones on, if there's something on Twitter, we need to look for it.
Okay, perfect. So I see here a first question from Babatuni Akinsami. Hello. What are the chances that this planet, the signal, is an harmonic of the one of Proxima B, so the Proxima B signal? Maybe I can start to answer that, and any of you feel free to comment and to add anything else. I would like to very briefly describe what an harmonic is, but I guess that's most people will know that, but if not, we are talking about a periodicity that shows up sometimes because of our sampling. And what that means is because of at the specific times that we take, that we observe the star, it can create some sort of ghost signals at periods that are usually half or twice or other multiples of a true period, of a true signal that is indeed in the data. And so the question here is, can this planet, can this signal that we attribute to Proxima D be an harmonic of the Proxima B signal, which is at 11 days? I would say you are asking what are the chances. I think, personally, I think they are low. we did a number of tests that allowed us to conclude that this is probably not the case. One of those tests has been that the evidence or the amount of confidence we have on this signal has been growing quite substantially over the months we observed this star. And what that means is, even while changing the sampling, the actual sampling that we did observations with. So I think we are very confident that this is not an harmonic of the signal caused by Proxima B. Indeed, we actually tailored our observations to try to get rid of these hypotheses, to make sure that this is not happening. And indeed, all the tests show that it's indeed not the case. Of course, we can never be 100% sure about anything, and about harmonics in particular. But I would say we are quite confident that this is not the case. I don't know if someone else wants to add
Yes,
to this answer.
If I can add something, I remember that when we first saw the presence of this signal in the data before the last campaign, this was one of the scenarios that I discussed with someone. I don't remember with whom, because if you did it, for example, you try to model the old HARPS data and some of our ESPRESSO data, having two planets at these periods and one eccentric planet at the 11 periods were sort of equivalent solutions back then, but that's one of the reasons why we increased the cadence of the observations to try to solve this degeneracy. And I think now we are quite confident there are two independent signals.
Okay, perfect. I hope that answers your question, Akin. Do we have another question? I see here that some people are asking us, is Proxima D, this new candidate planet, habitable? And that is short but very complicated question, and a very important question at the same time. As I told you, we have this concept of the habitable zone of a particular star, which is just in terms of distance to the star where water can be in a liquid state. This is a very, said like that, is a very simplistic concept, right? And you can imagine that, or I can tell you that for M dwarfs and stars like Proxima Centauri, things get more complicated than this simplistic approach. And so we don't have to just consider what distance we are from the star, but we also have to consider what conditions the star is actually, what conditions are available from the star at those distances. So just in terms of orbit, Proxima D is outside of this habitable zone. So outside, when I mean outside, is closer to the star than the habitable zone. And so just in that sense, it's hard to think that it would have the right conditions for habitability. But as I told you, things can change in M dwarfs, and some of these things, Alejandro will know much more about this, but some of these things that can change have to do with the activity of the star and what conditions that makes available for the planets, let's say. I don't know, Alejandro, do you want to add?
I would say that in general, the habitability of planets around M dwarfs, it's still an open question. There are a lot of fantastic works, theoretical works that have absolutely contradictory conclusions. And in this kind of systems that are so different than our own system, it's very difficult to reach very firm conclusions. But for Proxima D, I would say that unless there's some kind of life that likes eternal hellish days, eternal freezing nights, and probably not breathing, then it's most likely not habitable.
Or habitable by weird life, different life. Yes. We have another question from Dark Sapiens, which is asking us if there is a calculation of what kind of planets, in terms of their orbits and their masses, that are already discarded in the to exist in this system with the current data. Or so to add to that, could extra giant planets be still undiscovered, for example? And typically we answer this question. Maybe then I can let Mario comment if he wants to comment more. But we typically answer this question in the sense of exactly this: what kind of masses are we already sensitive to with the data that we currently have? And if we do that, we are almost sure that at short periods, any planets or any objects that remain in the system undiscovered would have to be very low mass objects, really low mass objects. So we are very sensitive to low masses at short periods with the current data. Then this sensitivity decreases with period, as we move away from the star. And so there we are less sensitive and so less sure also of what could be hiding in the data. I would say the chances are low that there are extra, especially giant planets, but I would say they are not zero. I don't know if someone wants to comment a bit on that. I called on you, Mario, but feel free.
No, I think you answered already this question, especially even concerning what can be in the outskirts of the system at the time of the work we did on Proxima C. We did not see any large signal in the radial velocities that could be explained with the presence of a giant. I'm here talking about, in particular, about some giant companion. But what we could model with the radial velocities turned out to be a signal related to a super Earth, so something smaller than something different from a giant planet. At the same time, so what can be more in the system? It's also actually a question that I would like to ask to all of you, because it seems that Proxima system is plenty of surprises, but with Proxima D, I think we already reached quite a very, at least with the data we have, we explored quite in a very good way the closest orbital periods. So I cannot exclude that something more can be of something small, small mass can be still in the system. And so maybe this is a good reason to go on with observations, and even to ask for other colleagues to examine the system in the next years.
Yeah, I would say it is very unlikely that there's anything of more than 1 or 2 Earth masses at periods shorter than 100 or 200 days. But also there are a few places in which probably the star would manage to hide them from us, like meaning planets with orbital periods very close to the rotation period of the star, or the harmonics of the rotation and things like that. But in principle, I would say that anything else that might be there is very small.
Yes, Alejandro, you mentioned one important point, the activity of the star that you were showing in the slides before. It's an ingredient. It's something really important to be considered when modeling the data, and the activity can be tricky and hide a lot of things.
I was going to add quickly that I think Mario's point and question is very relevant with these. The more questions we have, we answer, the more we come up with, and so this is a very good reason to keep keep watching what's going on these stars and on these planet systems. That's a very good motivation to do so. We do have a new question. What are the chances of Proxima D being tidally locked with the star? And so we should probably explain what tidally locked is. The idea here, maybe I can briefly explain it by telling you about the moon, and by telling you that you always see the same side of the moon, the same half of the moon. And that means that the translation period, so the time it takes the moon to go around the Earth, is the same as the time it takes to rotate around itself, and we end up always seeing almost exactly the same hemisphere of the moon. This is what it means to be tidally locked, and it's what happens on planets, typically on exoplanets that are close to their host stars. And in this case, Proxima D is indeed quite close to Proxima Centauri, as is Proxima B, the other planet in the system. And so I would say the chances here are quite high that that one or both of these planets are tidally locked with the star. What that translates to is indeed, as I told you, complicated issues for habitability, because that means half of the planet is hot, the other half quite cold, and so this has impact on the atmosphere, possible atmosphere of these planets, and therefore on habitability. But I would be happy if anyone wants to add to that explanation.
No, I think it was perfect.
So I would say the chances are high that
it is most likely tidally locked.
Alejandro asked us a question coming from Twitter. The question is it common for M dwarfs to host to host 3 or more planets as this probable system we found? So what are the statistics here? Alejandro, do you want to?
Yes, I can. I would say that the more we know, the more it seems that it is the most typical situations. in fact, I've seen a few works that say that from a formation point of view, the planetary systems of M dwarfs, in particular low mass M dwarfs, should be similar to the moon system of Jupiter or Saturn. So I would say that multiplanetary systems are the norm, and even close-in multiplanetary systems with many planets close to the star, and sometimes in resonant orbits. So in this regard, I think Proxima D just points us in the same direction that we were already going. And in my opinion, it says us that it's not that they are common, it's that it's probably all the systems have a lot of planets.
That is a very good answer, yes. And a very good pointing to the future, yes. Let's just find them all because they're probably there, these planets. So we have a question here. There's no more questions from the chat coming. So we have a question that is about the atmosphere or the possible atmosphere of these planets. We just lost Mario Damaso, who had to leave momentarily, but he might be back. But so the question is, any chance to detect an atmosphere on Proxima D on one of these planets? I would say there is a chance, but is a very small, is a very difficult task. If Proxima D or this low mass planet even has an atmosphere, it's going to be complicated. It's quite close to the star, and indeed its mass, its low mass, points to the likelihood that the atmosphere will probably not be very, very strong. So I would say I don't know how to elaborate better on that, but I would say the chances are low for this particular planet. But at the same time, there are future instrumentation that will help us, or that will go in that direction, at least. And
yeah, I think if there is a chance to detect atmospheres in the Proxima Centauri system, it's going to be on Proxima B or C, but we still need to wait a few years for the ELT and probably second generation spectrographs, and try to do some fancy high resolution spectroscopy with high resolution, high contrast imaging, coronography, and everything together, which is on the table, but we still need to wait a few years.
there is another question about, related more or less, about magnetospheres. Is there something we can say here?
Well, I think that theoretically this Proxima D planet is inside the Alphen radius of Proxima. So if this planet has a magnetosphere, there should be some planet-star interaction, which I'm not sure it's detectable. I'm just saying it should happen if the theory is correct. So if you remember, there's a paper from a few months ago that was observing M dwarfs within short orbit planets in radio, and they claimed increased radio emission for M dwarfs with short orbit planets. So maybe it's possible to detect something. I don't really know. I don't know if it's going to be, if there would be a signal, or if the signal is strong enough in case it exists.
Certainly asking for future studies about this planetary system. We have an interesting question about a neighbor of our stellar neighbor. Is ESPRESSO going to look for planets in Alpha Centauri, and either A or B, I would guess. So one of the other two stars on this triple system. Is it okay if I call on Francesco to answer this question? Would you be okay? Is ESPRESSO looking at AlphaSen?
Did we lose Francesco?
Yeah, I was looking for the button.
Sorry to call on you.
The microphone. I mean, this tool here is much more complicated than ESPRESSO. So yeah. So ESPRESSO is you mean at AlphaSen? Sorry, somehow.
Sorry to call on you like this. I was asking, or Felipe Murgas was asking, are we looking at the neighbors of Proxima Centauri? So is ESPRESSO trying to find planets around AlphaSen A or AlphaSen B?
Yes, exactly. So AlphaSen A has never been a very, let's say, good candidate because of different reasons until today, while AlphaSen B has been observed a lot actually already in the past with the HARP spectrograph from the LaCie Observatory. HARPS is the predecessor of ESPRESSO, and there are other groups in the world also observing AlphaSen B. And there has been a claim in 2011 that there would be a planet around AlphaSen B. In the meantime, it could be proven that this was most probably a real signal, but faked by the rotational period of the star. Still, AlphaSen B has been followed up. It is a difficult star, and I'm not sure that ESPRESSO is the best instrument to do it. It's so bright that you actually don't need a very large telescope to observe it. You need a precise instrument, but not necessarily as big telescopes as that. There is a second problem, or it has been a second problem, is that AlphaSen A and AlphaSen B are very close together in terms of image on the sky. So there is some light of when you look with the VLT or the other telescopes, you will have some contamination by AlphaSen A into the optical fiber with which you are observing AlphaSen B. And so you will get somehow not very clean spectra contaminated by the other star, which makes the whole observation more difficult. So in summary, ESPRESSO has not been following up AlphaSen B in that sense during the past years, because it was also the more difficult when AlphaSen B was the closest to AlphaSen A. So the short answer is no. The longer answer is that there are many reasons in favor or against, but that's not what we are doing right now.
So we just need to make ESPRESSO 2, put it in a smaller telescope, give it state-of-the-art adaptive optics and a very small fiber.
Yeah, that's certainly a little bit that. That's, by the way, what our colleague Christophe Lovis is trying to do with Ristretto, the Ristretto spectrograph, putting adaptive optics and linking it to a telescope to optically separate not only AlphaSen B from AlphaSen A, but in that case, the planet, so Proxima B, for example, from its star, such that you can remove this contamination and try to detect the atmosphere directly. So it's not what I would do with ESPRESSO on AlphaSen B, but these kind of considerations are being done exactly to try to observe the atmosphere, so that referring to the previous question.
Excellent. Thank you so much, Francesco.
Thank you.
It was a very, very good time. It was really a pleasure to be here. I think we should start to wrap things up. There seem to be no more questions coming from the chats, and so to wrap things up, let me thank first everyone in the team. This is a very large team of people that are doing a lot of work, and it's a pleasure to look at these, as Francesco said, these unbelievable, almost unbelievable results, and to see them showing up. And it's a pleasure to work with this large team of people. At the same time, thank you to everyone that followed us today and watched us today. Please feel free to join our social media accounts on Twitter, for example, and feel free to ask us any question about Proxima, any other planet, Espresso, anything you want to know. It's always a pleasure to answer your questions. And I think we can wrap this up. Thank you, Alejandro, Francesco. Thank you also to Mario Damasa for showing up. And maybe we can finish here.
Thank you, everyone. If I may say just one more thing before we finish, I would just comment that one of the goals with Espresso was to find a Earth mass planet in the habitable zone of a solar type star. And that's a really challenging goal. But I think results like this, getting a signal of just 40 centimeters per second in Proxima, it's showing that we are in the right direction. We are making progress towards that goal. It's going to take time. It's going to be difficult, but I think we are getting there.
I completely agree. So let's keep going in this right direction. And thank you again, everyone, for being here. And we'll see you in some other time. Thank you.